couple of announcements before we start the skeletal system. One is my policy is not to hand back exams until everyone has taken them. And since I've got a couple of people taking it tomorrow, then hopefully it will be Wednesday, assuming people don't get sick and things like that, all right? So I'll have exams back for you on Wednesday, all being well, okay? The other one is a personal request, because I have the opportunity to go to San Antonio to do a workshop with my teacher, my yoga teacher, who I haven't had a workshop with in 2 years, so that would be quite nice. But it means driving to San Antonio on the day that you have exam number 4. So I wondered if you guys would look at your calendars for me and see whether or not there's a time either later on the Monday afternoon or maybe on the Tuesday when we could meet and have the exams. So instead of having the exam Friday, have the exam the following Tuesday so that I can go to Texas. And if not, no. C'est la vie. It'll save me $400. So that'll be okay too.
What day is that?
I think it's
The 17th.
17th of April.
Okay.
So take it Tuesday?
Yeah, I was just wondering if there's a time when we can get together on a Tuesday or do it on Monday after class if people don't have, I don't know. So it's way up there. I don't have to book it yet, and I can book an Airbnb and then cancel it. So, but I just wanted to ask because last year she didn't come anywhere close enough to drive to, and it would be good to go have class with her. All right, so we are moving on. So the next exam comes up very quickly because we only do 2 chapters. All right, so we're going to do the skeletal muscle system and the nervous system, and then we will have the next exam. All right, so ignore point 3, I should grade that out. You do not need to know histochemical techniques for identifying muscle fiber codes. Don't worry about those, okay? Well, you guys might, but you'll do it in another class. So the rest of us don't need to know histochemical techniques. Right? And the reason we do these 2 kind of side by side, these 2 chapters, is that these 2 systems interact very, very closely. All right? So we often lump them together and call them the neuromuscular system. Okay? So hopefully you'll see over the course of the next week or so how they interact and how important they are to each other. So this should be something you recognize because you've all done AMP or kinesiology. All right, so I don't want to have to spend too much time going through the structure of the muscle. Pay attention to the epimysium and the endomysium and the perimysium because we'll find that those play a role in force production. Okay, and also try to keep in your head that the muscle is made up of lots and lots and lots of different cells, all right? And the cells are not at this level, like that isn't a cell, okay? This is not a cell. This is not a cell, okay? In there, these are cells, all right? So there's piles and piles of muscle cells within a skeletal muscle. Right? And I just want to point that out because it's sometimes we forget because we try to simplify the description of what's going on when we're moving, that there are multiple nerve endings and multiple different muscle fiber cells that are contracting. Okay? So, the connective tissue, the epimysium, runs into and coalesces into the tendon, and the tendon attaches to the bone. Right? Ligaments attach bone to bone, tendons attach muscle to bone. Okay? That's really important because that tendon transmits force production from the muscle to the skeleton and allows for movement, right? Because the skeleton can't move, okay? Fred and George over there can't move, can only move if you generate force and apply that force to the bone, okay? And this slide, I think, is a nice show. Okay, here's the perimysium, and then around each bundle of muscle cells is the endomysium. Okay. So when we're looking at the connective tissue first, as I said, they coalesce, they kind of scoop together, form the tendon, and attach to the muscle. That allows for transfer of the force from the muscle to the bone. The epimysium also allows, also stops rather, the spread of the signal telling the muscle to contract. Right? So we're very specific which muscle fibers we want to contract. Okay? And we don't want one muscle contracting and that electrical signal necessarily transferring to the muscle next door. Okay? Everything's got to be very precise. Uh-oh! What did you do?
I got stress fracture.
Oh, the tear. Good Lord, woman. Okay. Have a ball to put your foot up on. There we go, ma'am.
Thank you.
This connective tissue also is somewhat elastic, all right? It has a stretchability to it, which is why we can, stretch out our Achilles and stretch our patella tendon and things like that, all right? If it was solid, if it was stiff, we wouldn't be able to do that. So there's some elastic component to this connective tissue. And that acts like a rubber band, so when we stretch it, right, and then we release the stretch, it pings and adds extra force to the muscle contraction. Right? So if you stretch your fingers and you release them, they ping back up, right? Because you stretch the connective tissue, and then when you release it, it pings. Now, if I add squeezing my fingers at the same time as I release the stretch, I add extra force to that contraction. We do that a lot in school. We do it biomechanically because when we are being the most biomechanically efficient, we're applying these kinds of physiological laws to the biomechanics. So, when I pitch a ball, right, I don't pitch a ball like this, right? I pitch a ball by putting a big stretch on the chest and the front of the delt and adding force and the recoil of the rubber band at the same time. Make sense? We do it a lot in sport. Okay. So, We call it the stretch shortening cycle. Right? And one of the things that we also can do is deliberately elongate the muscle. So eccentric action on the muscle. So I control going down. That's stretching the patellar tendon, it's stretching the tendons across the hip joint, it's stretching the connective tissue on the quad, and then I can release that and contract my quad at the same time and add power to my jump. Right? So one of the times you might see this is when we do our vertical jump in lab. Okay? A vertical jump test is to test the power of the muscle, not the stretch shortening cycle. Right? So when we do a controlled vertical jump test, you have to wait at the bottom of the bend, allow this to relax a bit, and then jump so that the only thing adding to the jump is the power of the muscle. But if you watch basketball players do vertical jumps and train vertical jumps, they will work like this. Right? Because they want to include the stretch shortening cycle because they're going to apply it to a game scenario where I want as much power as I can achieve. Does that make sense? All right. So let me see. One of the things you'll see in the chapter, there's a box about stretching. I think it's on page 80 in this edition of the book. There's some recent research, relatively recent research, and we'll talk some more about it over the course of the semester. But what they're saying is that if you are a power athlete, you should not do static stretching before your power event, right? And the reason that they are suggesting that this might be something of interest is that what they find is that if they do a static stretch, hold that static stretch for a little while, and then ask that muscle to immediately contract, you see a decrease in force production. Okay? They think that the decrease in force production might be to do with the fact that you already stretched the connective tissue, and then you hold the stretch, and so the connective tissue starts to relax in the stretch, and then you don't get your stretch shortening cycle within the force production. Okay? I'm a little wary of that research at the moment because most of the stuff that I've read, and I readily admit I haven't read everything that's out there, because it is not my field of interest, so, but I'm a little bit wary just because a lot of what I've read doesn't seem to be very applicable to me, right? So, for example, if I'm a sprinter, right, and I'm waiting to go down in my blocks, then I could be standing there stretching my Achilles and my calf muscle, right, and doing a static stretch, and then if you watch them, then they shake out, then they go and get down in their blocks, then they're in their blocks for quite some time, and then they power out of the blocks and start running. That's not how the tests have been run in the lab, right? The tests are stretch, power, decrease in power. But the power that they're asking the muscle to produce is immediately after the stretch. Well, I don't know if that's realistic. So it could be that I haven't read enough. So if you read something that suggests that they're clearly showing a decrease in power. It's just whether or not it's really applicable in the real world is my question, not a question that the book asks. That's just what's going on in my head. Right? Okay, so again, hopefully the anatomy side of it is not new to you and you know what you're looking at. All right? This is the sarcomere. And the sarcomere is considered the smallest contractile unit within the muscle tissue. And the things that we want to be interested in, all right, are the Z line, okay, the actin filament. Note that the actin filament attaches to the Z line, because that's crucial for contraction, okay? Don't worry about the titin and the nebulin, that's in the calectamin, that's more than we need. Here's our myosin, all right? And we've got an overlap between the myosin and the actin proteins. And at the moment, at rest, we have a space between the ends of the two sets of actin proteins on either end of the sarcomere. Right? You can think of the sarcomere like it's a domino. And there's lots and lots of dominoes end on end to each other to make a muscle fiber. So those other proteins that I said don't worry about learning big long names, they act as like the lattice work. They don't move, they're not contractile, so they're not part of when we talk about muscle contraction, they're just providing like the framework for the sarcomere. They don't have a role to play that we know of at the moment within muscle contraction, okay? When the sarcomere shortens, okay, so when I do this and that muscle gets shorter, then what's happening is that those actin filaments are sliding over, they're being pulled across the myosin filaments, and that pulls those two Z lines closer together. So if you've got nice equipment in a lab, you can actually see that under a really powerful microscope, right? You can see that the Z lines get closer together. Okay? When it relaxes, we don't have any force involved in relaxing. Relaxing occurs because of the force of the limb, the weight of the limb, and because of gravity. And as it relaxes, we just see the sarcomere stretch back out and the Z lines get further away back to its resting state. Hopefully, you'll have a picture soon. So, actin. Actin is sometimes called the thin filament. Even on that previous picture, you could see that it was much thinner than the big bushy myosin filament. Okay? It's actually more than one protein wrapped together. Okay? So it's actually a wrap, almost like a helical wrap, of actin and tropomyosin, which is this long stringy one. And then there's a little kind of sticky site called the tropomyosin troponin. Okay? As a group, we call it actin. You just got to remember that actin is made up of those three different bits. When they're at rest, right, the actin has a receptor site on it. Okay? When the actin filament is at rest, that active site, receptor site, is covered up by the thin, stringy troponin. Right? What we see happen is that when it gets activated, the molecule shifts. And when it shifts, the troponin lifts off of the actin, off of the active site. The other protein that is contractile is our myosin filament, right? That's the thick bushy one, so it's often called the thick filament. Okay? The myosin filament is lots of these kind of double-headed tadpoles, right? Or double-headed sperm type looking things, okay? And they have these two globular heads which are made of myosin ATPase. Remember, our ASE is an enzyme. So this head, these two heads, are made of an enzyme that facilitates breaking down ATP, which is really useful because we need ATP for muscle contraction, right? We have a hinge joint here, and then this flexible tail. And so what happens is the flexible tails all intertwine and kind of lock together, and what we have is all these lumps of myosin ATPase sticking out on the sides. We call the head the cross bridge because it attaches to that active site on the actin. Okay? Which type of ATPase the heads are made of somewhat dictates how that muscle fiber can work. Right? So we'll come to talking about fast and slow, type 1, type 2 in a minute. If this is blowing your mind up, hopefully it's stuff you've heard before, but I have a very nice little animation that we may get to today or we may watch on Wednesday that will help a lot. So don't panic yet, okay? It's much easier when you can see it happening. Questions? So what we're going to be looking at, the interaction between the myosin and the actin, right? The myosin head, when the actin shifts, the tropomyosin moves away, the myosin head attaches to the actin, and then that hinge point, we break down ATP, and the head flicks. But because it's attached to the actin, it drags the actin with it. Right? Remember we said that the actin slides across the myosin, brings the two Z lines closer together. That's how that happens. Before we get to looking at that in more detail though, we're going to look at muscle fiber type. Okay? By the time you are 1 year old, your ratio of type 1 and type 2 muscle fibers is established. Okay? So the first thing you have to get through in your head is that whether you are fast or slow is genetic. Right? It is totally dependent upon how many fast twitch fibers, type 2 fibers, you were born with, and how many type 1 fibers you were born with. Okay? So most of us are born 50-50, and we're kind of not very good at anything. Or reasonable at everything, depending on whether you want to put a positive or a negative slant on it, right? If I'm going to be a world-class sprinter, I have to have a large ratio of type 2 fibers in my legs and my arms. Right? If I am going to be a world-class marathon runner, I have to have a large ratio of type 1 fibers, particularly in my legs. Okay? If I'm 50-50, and this is the bit that people don't like because we're told otherwise when we're growing up. Harry's smiling at me because he knows what's coming. Right? It does not matter how hard you work. It doesn't. Right? I know that we are taught, if you want it, just work hard enough, just try hard enough and you can get it. It ain't true. Sorry, not when it comes to physiology. Right? If you have a lot of type 1 fibers, you will never run 100 meters in under 10 seconds. It doesn't matter how hard you train. Right? You cannot change it. It's genetic. It doesn't alter with training. You have what you have, and the goal then should be to make the most of what you have. Right? But parents and teachers haven't quite got there yet. Right? They're all into, you can do anything you want to do, just try hard enough. Right? Okay? So, type 1 used to be called slow twitch. So just like the CPPC thing that we had it with the energy systems, if you are reading a resource and they are calling muscle fibers slow twitch, you need to check the resource because it might be outdated. Okay? Because we call them type 1s now. Okay? Type 1 fibers, slow to reach peak force production. So they take a while to contract and build up their maximum force. Okay? When they reach their maximum force, it is relatively, so the slow twitch is the orange, the type 1 is the orange. Their peak force is relatively low to type 2. Doesn't mean the peak force is low, because people who are type 1 are very strong. They can generate a lot of force, right? They just can't generate as much as a type 2. However, the benefit that type 1 fiber has over a type 2 is that they're very good at using system 3, aerobic metabolism, for making ATP. So they can make ATP forever. They can just keep going and going and going and going and going, right? Because they've got a lot of mitochondria. Okay? Remember that mitochondria is the organelle within the muscle cell where aerobic metabolism takes place. Right? So type 1 fibers have a lot more mitochondria than type 2 fibers. Right? And they've got some other adaptations that we'll see as we go on with this chapter that make them really good at using oxygen. So, because they create most of their energy via aerobic metabolism, sorry, I had a 20-minute lunch break today, my brain's like fried. They're really fatigue resistant, right? They don't get tired. They can just keep going, keep going, keep going, keep going. Okay? So they're really, really great for endurance performance. If I want to do cross-country skiing, if I want to go out into the wilderness and go backpacking, or if I just want to go for a long, long walk with my dog, or if I want to be, what event do you run? You run shorter though, don't you? 800. You're not really... kind of sitting on the fence there. Right? If I want to be a good 10K runner, right? Or I want to be good at cycling, then I'm going to need type 1s. Okay? Our other main division, our other main type is type 2. In the book, they will talk to you about several different types of type 2. We are going to stick with type 2A and type 2X. when you look at the chapter, they talk about type 2Cs, type 2Bs. Those other isolates have not been found in humans yet. They've been located in mammals and laboratory animals, but they haven't really identified them in human tissue. So we're going to stick with just the two, okay? Type 2s develop their force very quickly, right? They're able to contract really fast. And the force that they can generate is relatively higher than type 1. Right? But there's a downside. They're not very good at using oxygen to make ATP. Right? Particularly type 2X. They're pretty crap at using oxygen. Type 2A, they can use some oxygen, but they're not great. They're not like type 1s. So this means then that type 2 muscle fibers rely predominantly on ATP, PC, and glycolysis to make their energy. And as we've already seen in ATP and glycolysis, we don't get very long before we start to fatigue. Okay? So these muscle fiber types are really good for short, hard activities like throwing, jumping, sprinting. Right? So, don't worry about this part when you're looking at this in the book. Okay? What I want you to take home when you're looking at this cross-sectional slide, they've stained the muscle fibers different colors. Okay, so type 1s in this picture, type 1s are stained dark. In this picture, type 1s are stained light. But what I want you to take home is put this idea back with that kind of graphic of a muscle cut through and understand that one muscle has many, 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 many fibers, but those fibers can be different types. Right? So a muscle is not type 1 or type 2. Right? A muscle cell is type 1 or type 2. So how that muscle responds and the kinds of activities or events it will be good at depends upon the ratio between type 1 and type 2 within that muscle. Does that make sense? Right? So if you take that picture and go back to that picture, right? Every muscle cell doesn't have to be type 1. Some of them are going to be type 1, some of them are going to be type 2. Some will be type 2A, some may be type 2X. The ratio is the key.
How do you find the ratio?
Sorry?
How do you find the ratio?
They would have to do a muscle biopsy to actually, and then it's tricky because it's not the same throughout your whole body. So you might have legs that are type 1, predominantly type 1, and then have arms or back muscles that are predominantly type 2. So it's not consistent across the body. So genetically then, as I said, most of us are 50-50-ish, right? About 50-50. So, can I run a mile? No. If if my life depended on it, yes, I suppose, right? So, can I run a mile? Yeah. Can I run a mile quickly? No. Can I run a mile in under 4 minutes? Hell no. Right? Can I sprint 100 meters? Yes. It may take me 12 seconds to get down there, but I can sprint 100 meters, right? But I'm not very good at it. Okay? What we see, if we look at an elite endurance person, an elite endurance person is going to have somewhere around 70 to 85% type 1. So that's 15 to 30% type 2. Big difference. Big difference. Now, I am not suggesting that this person became an elite endurance runner because of this, right? This allowed him to become an elite endurance runner when he decided to put in the effort and the time and the resources and the rest of it, right? And do the work. But this person cannot be this person. It doesn't matter how much work they do. Right? If we're looking at an elite sprinter, we have a different picture, of course. Right? An elite sprinter is going to have 65 to 70% type 2s, which means we've got 30 to 35% type 1s. So again, very different picture to an average person, hugely different to an endurance person, right? And I can't train this. I'm born with it, right? The people that we see win gold medals and break world records are physiological freakoids. They're freaks, right? Even given the fact that a lot of them cheat, and they do, right? A lot of them cheat and take steroids or growth hormone or other drugs that they shouldn't be taking. They still have to work their buns off, right? And they were still born with something the rest of us don't have. Okay? So, it's a little disappointing, I know, but that's the way it goes. Okay? I can't jump for toffee, but I can bench press. Well, I could bench press, probably Molly when I was younger. Right? So it's an important concept to get your head around, okay? Because it makes what we're doing in lab that much more important. I have to be able to assess the individual that I'm working with. I have to be able to identify strengths and weaknesses if I'm a coach, right? Where do I put this person? Which position do I put them in? Okay? There's no point in putting this person as my winger that has to run down and catch the ball and get it over the line, because they're going to get overtaken by everybody on the field. I have to know that before I put them in that position and embarrass them. Not only in sport does this get used, it gets used in industry and in the military and in the medical world. Right? You don't want someone flying a Black Hawk who is they're not fast enough to react to what they have to do in that thing, and it costs millions of dollars. Millions of your taxpayer dollars. Okay? person that's flying it needs to have very fast reactions, and they have to have very fast twitch so they can respond to that reaction.
So does reaction time have to do obviously with the type 1 or type 2?
Response time, okay, all right, good question. And we have 2 minutes, so I'll go, it's a different class, but it's a great question. So, here's what we have. Okay, so we have reaction time, which is time of stimulus to initiation of movement. And then this is movement time, and this is end of response. Right? This is called response time. Now, what happens in sport and in everyday language and in the media is they call this reaction time, but it isn't. Right? So what you have, reaction time is genetic. Right? So we can test that in a lab with a setup where light flashes and you have to press a button. Okay? That reaction time is the amount of time it takes my eyes to see the flash, send the signal to my brain to recognize the signal, and make a decision what it's going to do to that signal. Right? That's reaction time. Then we have movement time, which is my brain sends a signal down the nerves to my muscles, and my muscles react. So this movement time is dependent upon type 1 or type 2. Okay? So when you're flying a Black Hawk helicopter, we want very fast reaction time and type 2s so that we can shorten the response time to any alert. Cool stuff, huh? Very cool stuff. Okay, I will see you on Wednesday.